And so this is some research I've been working on with Catherine for the past few years, focused primarily on the influences of Sagittarius on radio migration and mixing in the galactic disk. Wrong one. Yeah, so throughout this talk, there are really three main points I'd like to cover, which is what is radio migration and why do we believe this is a process that's happening in the Milky Way, and what role does Sagittarius play in this whole process, and how does it compare to other modes of radio migration? And then lastly, if it is playing a significant role, are there any potential signatures in the present day Milky Way that could be observable in chemistry? So first, thinking about radio migration, so if you have these orbits in axisymmetric potentials, they can serve three quantities. So first is the azimuthal action, which is equivalent to the z component of the angular momentum. And there's the radial and the vertical actions, which describe the oscillations in the radial and vertical directions, respectively. However, these quantities can change at resonances with non-axiosymmetric structures in the disk, namely spiral arms or bars. So, for example, at the co-rotation resonance, which is where the azimuthal frequency matches the pattern speed of the rotating structure seen here, you can have these massive changes in the angular momentum that are met with little to no change in the radial action. And so these are seen as examples of radial migration or churning in its purest sense. You can also have the opposite case when you can have changes in the radial action with no corresponding change in the azimuthal action. These are commonly referred as blurring, or in our case, radial mixing. And so, for example, here you see plotted here stars near the co-rotation of a spiral overdensity, and you see here plotted in blue. These are stars that are trailing the overdensity that are being pulled out. They're gaining angular momentum, while stars that are ahead of the spiral overdensity are losing angular momentum, and so they're migrating inward. And so if you were to plot this with the change in the angular momentum versus the initial value, these can appear as these ridges in these plots, which help you to identify the location of these resonances. So why do we believe this is something that is actually happening in the Milky Way? Well, first, it provides a very natural explanation for a number of observables, like the scattering and the age metallicity relation and the flattening of metallicity gradients. And there's a more recent result, I think this came out of Apogee, with the change in skewness from negative to positive skewness as you march out in the disk. And this is a weakening trend with galactic height, perhaps as these populations become less susceptible to the in-plane drivers of radial migration. So the next question we want to ask is, what about Sagittarius? So for those who haven't noticed, the Milky Way is currently undergoing a merger with Sagittarius. Sagittarius is a dwarf swirl galaxy. It's far less massive, and it's currently in the process of disruption. But its full history and its consequences for disk evolution are not well understood. And there's been a lot of great work investigating the vertical response to the disk through past encounters with Sagittarius. But we want to ask the question about the consequences for radio migration. So we use an in-body simulation of the Sagittarius-like encounter with a Milky Way-like disk. This is from a set of simulations from Shervin-Laporte, which cover multiple disk crossings since the present day. And so to address the question of what is its contributions to radio migration, we want to first model how can we best estimate that contribution. So we first we model the passes of Sagittarius as an impulsive encounter, and so by impulsive we mean that the encounter time between Sagittarius and the Milky Way is short with respect to the orbital period of particles in the disk, and that particles remain fixed to their disk crossing positions throughout the duration of the encounter. So to compute the impulse estimate, we first select particles that are in circular orbits prior to the encounter, and then Sagittarius emerges as a point mass for a time, and it applies a tidal force, which produces a tidal acceleration and an overall change in the velocity. So we can plot the r component of that change in the total velocity, which gives us an estimate for the change in radial velocity, which is plotted down at the bottom, versus the simulation response over the course of the simulation. And we can do the same for the angular momentum. We're taking the cross product between the position vector with that change in velocity vector to get and plot the z component of that change to get an impulse prediction for the change in angular momentum versus what you see in the simulation. And even though you initially probably wouldn't think of the encounter with Sagittarius as an impulsive encounter, the impulse approximation does seem to do quite well at reproducing the global quadrupole response of the disk to encounters with Sagittarius. So I think the next natural question to ask is, how does this compare to secular evolution? So after the first encounter, there's this long stretch of time where the disk is allowed to settle and relax, and it forms this two-armed spiral structure across the disk. And so during this more secular period, we can look at the change in angular momentum for circular orbits, and they sort of adopt this ridge-like structures similar to what we saw in those Sailwood and Binney plots. And that stands in sort of direct contrast to what we see during the encounter, where Sagittarius seems to interact with the disk in an inside-out like manner, where it causes significant changes in angular momentum in the outer disk, and that trend sort of gradually declines as you approach the galactic center. We can also look at the correlated response in migration and mixing. So look at the x-axis here, it looks at the change in the guiding radius for these particles that were initially on circular orbits. And also we can look at the radial excursion of those orbits at the end of the encounter. We can compare that to what we see during the secular phase as well. And I think what is quite apparent here is that during the encounter, Sagittarius seems to produce a correlated response in the disk between the migration and the mixing of stars, which isn't seen broadly systematically in the secular phase. And it doesn't really seem to have a strong dependence on where you are on the disk, like what we see during the encounter. So with that, going forward, what does this mean for the Milky Way today? Great. What does this mean for the Milky Way today? So from our present day snapshot, the most recent encounter with Sagittarius occurred around 500 million years ago at a pericenter crossing around 12 kpc from the galactic center. So this should have produced a fairly localized response in the disk. And since this encounter happened relatively recently, that motivates the question of whether or not there should be some lingering signatures in the disk that we can then look for. So we place a narrower emphasis on the solar annulus. So this is the present day snapshot for stars that are in the solar annulus plotting their maximum rate of excursion, like we did in the last plot, versus the change in guiding center since birth. And by birth, we mean since the time they were initially on circular orbits at some point in the past in the simulation. And they're also the particles are colored here by their disk origin. So the red stars are the inward migrators from the outer disk. The green stars are the outward migrators from the inner disk, and the blue stars are ones that have an origin within the solar annulus. And what should be quite apparent here is that this correlated response that we saw earlier from the first encounter between the radial excursion and a guiding center also persists from the most recent encounter as well into the solar neighborhood. And though this is a good sign, however, the y-axis here tells us about a present-day property of the orbit, while the x-axis tells you about the history of the orbit. So we want to take this and translate this into a space where, at least in principle, both of the axes could be measurable or reflect a present-day property of the Milky Way. And so to get there, the first step we did was we imposed an age-dependent negative metallicity gradient, which just means as we're selecting these circular orbits throughout the history of the simulation, we apply a metallicity to them that changes with time. And once we have that, we can also compute azimuthal variations for stars at a common radius. So by that, we mean we should sort of take sort of a radial bin and compute the mean metallicity within that bin and subtract that off the metallicities of stars in the radial bin. You get the azimuthal variations. And these azimuthal variations should correlate to this change in angular momentum. And if the dominant trend in your disk is a negative metallicity gradient, as inward migrators should on average be more metal poor, and the outward migrators from the inner disk into your solar annulus should be more metal rich. So if we were able to swap out that x-axis here, which is the change in guiding center with the azimuthal variations, we're still able to retain this trend that we saw earlier between the x and y axis, but in terms that describe present day properties of the stars within the solar annulus. And so we find this to be quite interesting, and I think getting us on the right path towards saying something potentially predictive about the present Milky Way today. So with that, thank you, and I welcome your questions.
Great talk. Really interesting stuff. I'm curious how, so with this plot here, these populations look very overlaid, right? Am I right? So the green seems very coincident with the blue. The blue seems pretty coincident possibly with the red, unless the red is distinct and not behind the blue, as it looks to be. How would you go about kind of actually distinguishing these things as observables? Or I guess, I mean, if they're outer disk, inner disk, in situ, is that how you would just kind of assume that sorry. How would you go about kind of distinguishing between these populations, and like with what level of confidence can you do that when they're so overlaid?
Right. Yeah. So that's definitely that's a good point. They are quite overlaid, especially the inner disk populations and the in situ populations. However, what we do think is quite noteworthy is the inward migrators from the outer disk seem to be highly eccentric and tend to be quite metal poor on average. So if you're looking sort of in this region of the space, the inward migrators, I think, do sort of occupy a unique region that could be worth, which could be an area where they are distinguishable from the outward migrators or the in situ stars, and it seems to have sort of a correlation there as well.
Thank you.
Could you please explain why we would expect a correlation between these two quantities to come from the passage of Sagittarius? Like, why does it introduce a correlation between delta JR and delta J phi?
Yes, great question. So actually, if you go, I should back up from this mic. If you go back to these plots here, which show the simulation response to these past encounters and also the impulse prediction, the areas of the disk which experience sort of the significant changes in angular momentum also tend to correspond to the areas that experience the greatest amount of change in their radial velocities. And so these are those populations are preferentially in the outer disk are being not only torqued quite significantly, but also heated quite a bit. So that's why you get this correlation between these two quantities, and that's why it appears in this case for the first encounter, and this also applies to the most recent encounter as well.
Okay. Thanks.
This might be like just talking shop, because I did something kind of similar, but not with Sag. And one of the questions I had was like, how do we actually define what is migrating? So what is your definition for migrating here?
Right. So for
Katie.
So the word radial migration has been completely mangled in the literature. I agree with this, and I'm in part contributing to that. So initially, this idea of radial migration, like you go back to like Sullivan and Binney, like 2002, like radial migration, they were describing it purely in terms of what happens at co-rotation with spiral arms, where you have an increase you have a change in the angular momentum without an additive contribution to like the random energy of those orbits. And so that was originally what was referred to as radial migration. So from that point, that term has been changed and added on quite a bit since then to apply to any change in angular momentum, or even, I think, the most radical people, any change in radius, which you did that? Okay, so yeah, and so so blurring is another way. I think it was an attempt to add some order where blurring typically referring to sort of a change in the axis and to the heating of the orbits, while churning referring to the migration of like the guiding center of the orbit. I think that's at least a good way of trying to distinguish between the two. And if you're talking specifically about just changes in radius, then I think other people have used like radius migration, like as a description of that, as opposed while keeping radial migration to be preserved for what it was intended to be, which is just changes in the angular momentum without a corresponding heating. Oh yeah, absolutely. We might add a table in the paper, which sort of defines all these terms clearly. Yeah. Also, this is work we're working on now. So be on the lookout for any future publications on the subject.